Okay, well, welcome again to our journey into number theory, and we're looking still at the topic of squares. We've dealt with sum of two squares. We had a look at some Pythagorean triples and their application to Fermat's last theorem for n equals 4, and we now move on to the sum of three squares. So we've seen that certain numbers can't be written as the sum of two squares, in particular primes that are 3 mod 4. And there are numbers such as 15 that can't even be written as the sum of three squares. You need 4 squares for that. So we'd like to characterise when a number can be written as the sum of 3 squares. And a little lemma to that tells us that if x is a 7 mod 8 number, doesn't got to be prime, but if x is congruent to 7 mod 8, then x cannot be written as the sum of 3 squares. And the proof of that actually is very simple, so I'll just quickly go through that here. So if x is a number which is 7 mod 8, then it's not the sum of 3 squares. Well, suppose it is. Suppose you've got a squared plus b squared plus c squared. Now, you put your mod 8 glasses on, you read everything modulo 8, then you start squaring. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 1, 4 squared is 0, 5 squared is 1, 6 squared is 64, which is 4, 7 squared is minus 1 squared is 1, and that's it. So the only squares you get are 0, 1 and 4 modulo 8. So if you now try and pick 3 of these and add them together, well, you might pick 0, 0, 0. That'll give you 0 mod 8. You might pick 0, 1, 1. 0, 1, 0. That would give you 1. You might pick 1, 1, 0. You get 2. You can pick 1, 1, 1. That gives you 3. 4, 0, 0 is 4. 4, 1, 0 is 5. And 4, 1, 1 is 6. But you can't get 7. You can't make 7 by taking 3 of these. And so our number was x was congruent to 7 mod 8, so we immediately have a contradiction. So 7 mod 8 numbers can't be written as the sum of 3 squares. Now, what's the full story? Well, that's our next theorem. Is the full story of this is as follows. It says an integer n can be expressed as the sum of, at most, because you can sometimes get away with 2, can be expressed as the sum of at most 3 integer squares, unless n has that shape. That is, unless n is a power of 4 times a number of the shape 8k plus 7. So we've seen in that lemma, we've seen that if alpha is 0, if n is 8k plus 7, it can't be. And now this says, well, it can't be if it's any multiple of 4 times a number which is 8k plus 7. Now the proof of this is it's not that difficult. I mean, we can have a look at the proof, which I've written out here. So let us suppose that we've got our n is of this shape. It's a power of 4 times 8k plus 7. We've got to show it's not the sum of 3 squares. Now the converse, which I'm not going to do here, is much, much harder. That is, to show that if a number is not of this form, then it is the sum of 3 squares. That is very difficult. And in fact, you'll probably, if you hunt through number theory books, it's very hard to actually find a proof of this. I believe it goes back to Gauss, was the first to do this, and his proof is very clever but quite complicated. And I think you need to look at far more advanced books before you can actually find a proof of this. Most books do what I'm doing here, is they just skip over it and say the converse is much harder, and we won't do it here. However, I'm just going to show here that a number of this shape is not the sum of 3 squares. So again, to get a contradiction, we suppose it is. And so firstly, we observe that if 4 is a factor of this, then either all these numbers have to be even, or exactly 2 of them are odd. You can't have one of these odd and then 2 even, because that would give you an odd number here and it won't be divisible by 4. So there are only 2 possibilities. If 4 is a factor of this, there are only 2 possibilities. Then all of these are even, or exactly 2 of them are odd. So without loss of generality, we may as well assume that, say, in the second case, let me assume that x and y are odd and z is even. Well, in that case, when you square an odd number, you get odd. So modulo 4, x squared would be 1. When you square y, also you get 1. And when you square z, you're going to get 0 mod 4, if z is even. And that gives you 1 plus 1 plus 0 mod 4, which is 2. And that is impossible because the n we started with, you'll recall, was this thing. And this n is 0 mod 4. And in this case we get 2 mod 4, so that's impossible because n is 0 mod 4. So, of the 2 possibilities, we've just wiped out this one, and that means x, y and z must all be even. Well, if they're all even, then you can divide them by 2. So that is, I can take the original equation for n, and I can divide both sides by 4, and then write that as x over 2 squared plus y over 2 squared and z over 2 squared, and these are integers because these are all even. And so what I've now done is I've taken a number, I've taken the original number divided by 4, and it is the sum also of 3 squares. So I can just keep repeating the process until this powers of 4 gets smaller and smaller until alpha is 0. And then we end up with 8k plus 7 is the sum of 3 squares, but by the previous lemma that was impossible. And so that shows that a number of this form, 4 to the alpha 8k plus 7, cannot be written as the sum of 3 squares. And as I mentioned, the converse of that is also true, but much harder to prove. Well, just to finish off, how far do we have to go? Well, it turns out that 4 squares are sufficient. So the following theorem, which was due to Lagrange, completes the story on the sums of squares. Again, I'm not going to give the proof here. There are plenty of textbooks that do this. It's quite a long proof, and there are various ways of doing it. You can get it from an interesting generalization of complex numbers called quaternions, and using the identities similar for complex numbers, using the modulus or the norm, you can have a similar thing for quaternions, and from that you can get the following, I think, rather amazing identity, that if you've got the product of 2 lots of sums of 4 squares turns out to be itself the sum of 4 squares, and this explicitly tells you what the squares are. So this tells me if I've got x and y are the sum of 2 squares, then so is their product. And then with a lot of work you can prove finally Lagrange's theorem. Every integer can be expressed as the sum of at most 4 squares. Every integer. So you don't need to go beyond 4. I state again without proof the number of representations of n as the sum of 4 squares, counting signs and order as being different, turns out to be you take the sum of the divisors of n, but not n itself. Sum of the divisors of n, except for 4 can't divide that divisor, and you multiply the sum by 4, and that gives you the number of representations. So you take all of the divisors of n, except those which are divisible by 4, add them all up, multiply by 4. Again, proofs of that, I think this again goes back to Jacobi. Proofs of this are in some number theory books. Well, famous problem called Waring's problem, which first stated goes back to about 1770. So having dealt with representations of sums of squares, it's natural to ask about higher powers. For example, it's known that every integer can be written as the sum of at most 9 cubes. Now, in fact, these numbers, 23 and 239, are interesting numbers. All numbers, of course, are interesting, but these two are particularly interesting because these ones actually require 9 cubes. So to write 23 as the sum of cubes, it has to be 2 cubed, 2 cubed, and then 7 lots of 1 cubed. And 239 is done in a similar way. It also requires 9 cubes. Now, in 1970, which is mathematically quite recent, it was shown that every integer can be written as the sum of, at most, I should say here, sum of, at most, 19 fourth powers. So something odd, something funny is going on here. These are interesting numbers. We need 4 squares, we need 9 cubes, we need 19 fourth powers. Well, what about fifth powers? Well, I think it's now known that it requires 37 of these. So let me get some notation going here. So for every positive integer k, we let gk be the minimum number of kth powers required to represent every integer. Or equivalently, we want the smallest number g of k such that x equals this has integer solutions for all integers x. And the obvious question is, can we find a formula for this? Well, no such formula is known, and the problem is generally called Waring's problem, and it was first stated in print, I believe, in 1770. Now, what can we write down? Well, we've already seen that you need 4 squares to represent every number. So if you're representing numbers as squares, you need 4 to represent every number. That was our Theorem 1.1. It is known that you need 9 cubes to represent every number as a sum of cubes. You need 9 of them. You need 19 so-called biquadratics or fourth powers. So if you want to represent every number as a sum of fourth powers, you need 19 at most. And g of 5 turns out to be 37. I mean, at first glance, when you see 4 and 9, you think, perhaps squares, but then 19 upsets you because it's not a square, and then you look for patterns on this that are not immediately obvious what the next number is going to be, and so on. So as we've seen in the examples, for fixed k, only certain numbers, once you fix these here, only certain numbers actually require that many terms. So, for example, for cubes, it turns out only 23 and 239 actually need 9 cubes. So these are in some sense very special aberrations in some sense. Now, I'm going to, out of the air, just pull this funny looking number here, and you'll see where it comes from a little bit later, but I'm going to take n to be a number of this shape. So I take 3 over 2, raise it to the power k, take the floor, multiply by 2 to the k, and subtract 1. So here, this is the floor of x, denotes the greatest integer less or equal to x. Now, by the way, if you put k equals 3 into this formula, you get n is 23. And that should get you excited here, because we saw that 23 was one of the numbers that needed 9 cubes. So this number n then is an attempt to find the worst case scenario for each k. It's not known that it is the right one. I'm just simply saying here that it happens to match nicely, at least, with k equals 3. Now, what I'm going to show here is that we can write this n. Well, let me just go through here. So also note that if n is less than this, so all I've done there is I've just forgotten about the floor. So I don't take the floor, I just take 3 halves to the k times 2 to the k minus 1. This won't be an integer anymore, but n will be less than that. And again, I can toss away the 1, and so it's less than this, and that collapses down to 3 to the k. So that tells me to represent this n as the sum of kth powers, we need each of the numbers xi to be less than 3, strictly less than 3, i.e. only less or equal to 2, that is noughts and ones. So when I try and write this number as the sum of kth powers, then the powers will have to be of 1 or 2. Now we need, from what we've got here, we need that many lots of 2 to the k. So it's this number minus 1, because of the minus 1 makes this smaller than that number. And that leaves that many lots of 1 to the k. So in other words, I can write n as this many numbers, this many multiples of 2 to the k. So it's 2 to the k plus 2 to the k plus 2 to the k that many times. And then plus 1 to the k that many times. So 1 to the k, 1 to the k, 1 to the k that many times. So in order to write n as efficiently as possible as the sum of kth powers, they have to be powers of 2 or kth powers of 2 or 1, that many of each. Now, how many terms does that involve then? Well, that means it involves that many terms plus that many terms, which is this number. So that means then my g of k, because I've constructed these particular numbers that require this many terms, my g of k must be at least as big as this. And I'm going to call this function here L of k. And now for the exciting bit. If you take this thing here, L of k, and you plug in some values of k, you get L of 2 turns out to be 4, and that's g of 2. You plug 3 into here, it turns out to be 9, and that's g of 3. Could be happy accident at this point. You plug in 4, you get 19. There's the formula that's giving me the 19, which is g of 4. And L of 5 is 37, which is g of 5. So it looks like, we don't have a proof, but it looks like this is the right formula for g of k. But no proof has been found. So that still remains an unsolved problem to find exactly what this g of k is, and perhaps this L of k is the right one, we don't know. So the related function g of k gives the minimum number of kth powers required to represent all sufficiently large numbers. That is, we ignore these aberrations. In the case of k equals 3, we ignore 23 and 239. This is also an important function. Well, clearly g of 2 is, capital G of 2 is little g of 2 is 4. And it is known that capital G is somewhere between 4 and 7. Remember, little g of 3 is 9. Capital G of 3 is somewhere between 4 and 7. And it is known actually that g of 4 is in fact 16, which again is less than the 19 that we have for little g of 4. Beyond that, only bounds, I believe, for these values are currently known, but people are adding new information to this all the time and working on these problems. Well, that is the end of chapter 1, and in the next chapter we're going to start looking at just some very basic analytic number theory. We're going to start looking at the little bit on the distribution of primes, introduce pi of x, and Bertrand's postulate, and the Euler expansion.